and today we're going to have a little look at enzymes. So the first thing you need about enzymes is they are biological catalysts, which just mean that they speed up a bunch of chemical reactions in your body. Enzymes are a bit weird though. They don't just break down anything. They're very, very, very specific. And I would like to use Pac-Man when I talk about enzymes because Pac-Man is just great. So the first thing you need about enzymes is that they've got this thing called an active site, and that is where the substrate, so the thing that is being broken down, the substrate, fits in. As everyone knows, Pac-Man likes to eat power pellets. So the power pellets, the substrate, will fit inside the active site and will then get broken down. But the active site is very, very, very specific to whatever it is that the enzyme will break down. If something comes along that doesn't fit inside the active site, then the enzyme can't break it down. So unless Pac-Man eats a special power pellet, he can't break down ghosts. He can't eat the ghosts. So here's Pinky. Pac-Man can't break it down. Pinky doesn't fit inside the active site. The power pellet does, so that will fit in there and the enzyme will break it down, but a substrate that doesn't fit inside the active site because it's not the correct shape won't get broken down. You need to know three things that are going to affect the rate of reaction for an enzyme. So one of the things that affect enzyme activity is pH, and you should be familiar with the graph. If you've got enzyme activity on the y-axis, so the higher we go up on the y-axis, the higher the enzyme activity, and then down on the x-axis is your pH. And then the graph you'll find will look something like this. So as the pH increases, so does the enzyme activity until we reach the top bit here, and this is called the optimum pH. Optimum pH. So that's the pH on which the enzyme works best at. All enzymes will have their own optimum pH. Some enzymes that exist in the stomach will have a optimum pH slightly more to the acidic, so somewhere around 2 or 3, whereas enzymes found in your intestines, where it's slightly more alkali, will have a slightly higher pH towards the alkali side of the pH scale. But then, as you can see, once we reach past its optimum pH, the enzyme activity starts to decrease. All depends on what kind of question you are asked in the exam. If it says describe the effect pH has on enzyme activity, you need to be very, very specific. Use data from the graph. So and we'll say that the optimum pH here is 7. So as pH is increasing, enzyme activity increases until it reaches the optimum pH. You need to make sure that you use the term optimum pH of 7. So enzyme activity is increasing as pH increases. Up until 7, it's optimum pH. And then after pH of 7, enzyme activity starts to decrease. Now, if it then asks you to explain the effect of pH on an enzyme, you need to mention the active site. So going back up to our Pac-Man, the active site where the substrate fits in this little bit here, the active site, that will change shape. So what might end up happening is Pac-Man's face may now look like so. So this is our active site. However, because it's changed shape, the substrate can no longer fit in there. So the active site has changed shape. The enzyme has denatured. You can't say the enzyme's died because it wasn't alive anyway. The enzyme has denatured. So it no longer works. Enzyme has denatured. You need to use all of those keywords. So if pH is too high or too low, the active site changes shape, therefore the enzyme is denatured. And if you want to go in slightly more detail, the reasoning that the active site changes shape is because the bonds holding the enzyme together start to break. So at the extreme ends of the pH scale, the bonds start to break, the active site changes shape, the enzyme's denatured. Very, very similar if you look at temperature, another factor of enzymes. And we can draw another little graph. And this time it's going to be temperature. Up here, so as we got the y-axis, temperature increases. No, done it wrong. Temperature's not there. Enzyme activity is there. Enzyme activity goes up. So the higher we up on our y-axis, the higher the enzyme activity. And down here, then we've got temperature. So the longer we get across this way, along our x-axis, the temperature increases. And what you'll find is a graph looking very similar to this. So again, if the question says describe the shape of the graph, as temperature increases, so does enzyme activity. This is because it's so at the cold end, there's not enough energy, so neither enzyme or active site actually move around. So they're not. So the going back up to our picture up here, the substrate's not going to move, so it's not going to go into the active site because it's not moving. They're not going to interact. And like our pH, there's always going to be an optimum temperature. Most of the time, optimum temperature is about 37. I'll give you a couple of seconds to have a little bit of think as to why that's the case. And you guessed it, it's because body temperature is 37, so the optimum temperature of enzymes in our body is 37 because of our body temperature. And my cat's trying to get into my room. But past the optimum temperature, enzyme activity starts to drop, and that's because, once again, those bonds holding the enzyme together start to break, so the active site changes shape, so the enzyme is denatured. So we can kind of see a little bit of a pattern that the wording we need to use is something about active site changing shape because the bonds are being broken, so the enzyme is therefore denatured. Remember, it's not dead because it was never alive to begin with. And the last thing that's going to affect the enzyme activity is substrate concentration. So again, if I draw the graph, and this time I know that enzyme activity is on the y-axis, activity, and substrate concentration is on the x. So again, the longer we go along the x-axis, the more substrate there is. That's what increasing substrate concentration is. And for a time, as you increase substrate concentration, there's going to be more enzyme activity because there's more stuff, there's more substrate to break down. So the reaction's going to go faster because there's much, much more likely for our substrate, going back to our Pac-Man here, our substrate to actually meet with the active site to form what's called an enzyme substrate complex. I'll spell that once I sort my camera out. There we go. There. It will form an enzyme substrate complex. And that's when the can't see it. The enzyme substrate complex, and that's what's formed when the substrate meets with the active site. It forms an enzyme substrate complex. However, there's only so many amount of enzymes, and once all of the active sites are full up, then enzyme activity cannot increase anymore. So, describing the graph as enzyme substrate, as substrate concentration increases, the enzyme activity increases until a certain point where enzyme activity doesn't change. Explaining the graph, slightly more complex, as substrate concentration increases, enzyme activity increases until a certain point, and if they give you data, make sure you include that. This is because, so the reason that's increasing is because the substrate is more likely to come into contact with an active site and then get broken down. However, once all the active sites are full up, then substrate concentration is not going to have an effect on the enzyme activity in the slightest, which is why it levels out here. That is a very, very quick crash course on enzymes and the three things that affect them. So temperature, pH, and enzyme substrate concentration. Keywords you need to use when answering these questions is changing the shape of the active site, the enzyme denaturing, and if you can get enzyme substrate complex in there, bonus points. And here's my cat, Saria. She likes a good old belly rub. Ooh. Thanks. That's just what I needed. Thank you all.